Okay, the first thing we have to do in this exercise is to calculate the Taylor polynomial for the 4 around 0 of this function here. Okay, and given the result, we have to decide whether f has a local maximum, minimum, or inflection point at this point x equal to 0. All right. This is much easier than it looks because although in principle it seems that we should do the whole expansion by taking derivatives and substituting into the formula for the Taylor polynomial, we don't, because we know the expansion of the sign. We know that the sine of x is equal to x plus ox when x goes to 0. So f of x is 1 plus x cubed multiplied by this, so x4 plus ox4 when x goes to 0. And that is the fourth, or the polynomial around 0 of x. So this is 1 plus x4. Now, can we conclude anything from this about whether f has a local maximum, minimum, or inflection point at x equal to 0? The answer is yes, because this is telling you what is the local behavior of this function around 0. What this is telling you is that the function near 0 behaves like this. It's almost parabolic. This is 1, right? This point is 1 because at x equal to 0, this is 1, right? It is symmetric, all right? Locally, right? This is locally. I mean, further away from 0, it doesn't behave like this. It oscillates because it's multiplied by a sign. But we don't care about that. We care close enough to the point 0. And we have a parabolic-like shape like this. This is not parabolic because it's x4, but the behavior is the same. It's like this. So clearly, this has a minimum. There is a minimum, a local minimum of the function there, right? You can also prove this in a more rigorous way, because the conclusion of this being the polynomial is that f prime is equal to f second and is equal to f third at 0, and all three are equal to 0. Okay? Since f prime is equal to 0, then we know that the tangent is horizontal there. So it can be, the point this one can be a maximum, a minimum, or an inflection point, right? That depends on which is the first non-zero derivative. But you see, the coefficient of the fourth power here is 1, which means that the fourth derivative at 0 is 4 factorial. So 24. And 24 is positive. So it turns out that the first non-zero derivative beyond the first is the fourth, which is an even derivative. And if it is an even derivative, then the function at this point is either convex or concave. It doesn't have an inflection point. And since this is positive, it has to be convex, like here, right? And given that the derivative is also 0, the first derivative, then this has to be a minimum. So the function has a local minimum. So either way that you look at it, either because the approximation, the local approximation of the function is this function, which is clearly has a clear minimum here, or because you derive from the expression of the polynomial all these derivatives, which is what you need in order to calculate to determine what happens with this point. Either way, the conclusion is the same. There is a local minimum of the function at this point.